So we've covered a lot of material in this chapter so far. What I'd like to do is cover compressible flow. Okay? So compressible flow. Here's an image. It's a photograph that somebody in the Navy took about a Navy fighter or aircraft. And you can see that it's approaching or breaking the sound barrier. That white halo is formed by the water condensing droplets in the shock wave. And it's coming off of the aircraft at different locations where it actually is exceeding the Mach 1. So you get a shock wave there. This was grabbed off of the internet somewhere. Okay. So there's a whole class. I think it was taught last semester. I think Butler taught it, compressible flow and propulsion systems. Or this semester?
Last semester, Maldonado taught it.
Maldonado. And I encourage you to get into it. This is a prereq. I hope it's a prereq for the class. I never did look, which is crazy.
It should have been.
And so this is our little introduction to compressible flow. All right. What are the SI units of thrust? First clicker question. I'm going to start this up. Everybody's in. We'll stop. And 100%, please. I earned my pay. I have earned my pay. Another clicker question to get us warmed up. And the question is, can a rocket produce thrust in a vacuum? Yes or no? Couple more seconds. We're in. I'm going to stop and show the results. Yes, you can produce thrust in a vacuum. This man we should know a little bit about, Robert Goddard. He lived from 1882 to 1945. What ended in 1945? World War II. He is the American father of modern rockets. Propulsion in space, but actually to get to space, rockets are used. He was originally out of Massachusetts, out of Worcester, Mass. Here's a picture of him, probably in the 1910s, 20s. With the early model rockets he was shooting up in the air. Now, when you shoot rockets up in the air, they do come down, and when you go higher, they come down maybe further away from where you launched them. So he had to move away from Worcester. He was doing a lot of testing there, but he actually ended up testing a lot out in New Mexico, I believe. But he's so popular that we now have the NASA's Goddard Space Flight Center located in Maryland. And there's a lot of employees, NASA employees, that work at the NASA Goddard Space Flight Center. There's a popular book. It's an easy read, actually a good book. It's The Rocket Man, Robert Goddard and the Birth of the Space Age. I think it was published in 2004. And this I grabbed off of Amazon. Also in 1964, they honored him by putting him on a postage stamp. That's usually a symbol of honor, respect, and all that. So there he is. But he wasn't always honored. In 1920, the New York Times published a front page article on believes rocket can reach moon. Incredible. The day after that front page story ran, some unassigned or unsigned New York Times editor wrote a severe strain on credulity. So it's like, I don't believe it. And here's some quotes out of it. That Professor Goddard does not know the relation of action and reaction, and of the need to have something better than a vacuum against which to react, to push against. The idea is if you're going to go faster, you need to push against something. And so if in air, great, you can push against air. But if you're in a vacuum and you want to go faster, you got to push against something. Hey, there's nothing to push against. Ain't going to go. Action, reaction. Of course, he, Professor Goddard, only seems to lack the knowledge ladled out daily in high schools. They since retracted that editorial with an apology, but at the time he was ridiculed. Anyway, that's an interesting little tidbit about Goddard. Well, we want to talk about things that go fast. And when you have things that go fast, you have to worry about the compressible effects and also the speed of sound in material. So what is the speed of sound? Is it defined in a gas? Yes. Is it defined in a liquid? Yes. Is it defined in a solid? Yes, it is. But it's defined in any fluid. It's the speed of the propagation of a pressure pulse. And so this C is the letter used to designate the speed of sound or the sonic speed. Somebody asked me, what's the difference between the sonic speed and the speed of sound? No difference. It's just it's the same. So the square root of the derivative of pressure with respect to density holding S constant. Now, when you have air as your fluid, and we do a lot, that's what you're hearing right now, my voice going speed of sound to your ears. And the speed of sound is equal to, you can work it out, square root of KRT. I did work it out, and you can look at that video, and I'll talk a little bit about it. Not to skip a lot of stuff, but there's a lot of material I put on the internet as well as also in the textbook that you can read for more details. What is K? The ratio of specific heats. What is R? Gas constant for that gas, R bar divided by molar mass. What is T? Temperature. If I put in negative 20 degrees C, I have the square root of a negative 20. It's not going to work, so it has to be absolute temperature, Kelvin. So as the temperature of the air goes up, what does the speed of sound do? Does it stay constant, or does the speed of sound go up? It goes up. As the temperature of the air goes down, the speed of sound decreases. Let me ask you this question. Should I have it a clicker question? As pressure goes up, how does C change? It's either A, unchanged, so it's a constant, not changing, or B, the speed of sound goes up, or C, the speed of sound goes down. So we just talked about temperature. Now I want to know the effects of pressure. So now I change pressure. That's my question. Does the speed of sound remain unchanged? Maybe I should do it like that. Unchanged. Or in air, if I increase the pressure, the speed of sound increases. Or if I increase the air pressure, the speed of sound decreases. Which one is it? All right, let's go ahead and call the question. And let's check our votes. All right. So this is restricted to air, true? We're talking about air. I know I could talk about the speed of sound in liquids and solids, but I've said, no, let's talk about air. The temperature in air goes up, the speed of sound in air goes up. As the pressure goes up, what does the speed of sound in air do? Well, a lot of you say it goes up, but let's take a look at this equation. Is this equation true or false? True. Okay, K. Tell me a little bit about K. 1.4 ratio of specific heats. If I increase the pressure of an ideal gas, does K change? It's constant. How about R? It's kind of given in the name, ideal gas, constant. Not a function of temperature, not a function of pressure. And how about temperature? As I increase pressure, does temperature change? No, it's a different beast. Okay, now I may do some work to, adiabatically and isentropically compress some gas to boost the pressure, but then the temperature is changing as well. That's not the context. You can leave temperature alone and raise raise pressure or lower pressure. True? Yeah. So there's separate properties. Aren't they often two independent intensive properties used to fix the state of certain fluids? So, what's the correct answer, Professor? A. True? All right. Now, how many have heard of the Mach number? Mach number. True. Yeah. So, the Mach number is the ratio of the actual speed of something typically in the air compared to the velocity of sound or the sonic speed in the air. Okay? So you can have an object, a bullet, a piece of chunk of metal being flown as a projectile, or an aircraft going very, very fast, and actually even a rocket exceeding the sound of speed in the air that it's flowing through. It can be traveling at a Mach number greater than 1. True? Yeah, that was hard to do. The equation that's what we derive is a little bit of a derivation. Let me give you a quick go through, but right here is the bottom line equation where the speed of sound squared is equal to the rate of change of pressure with respect to density holding S constant. All right, so what you do, and it's outlined in the textbook, is think about a piston that is abruptly moves in a tube containing stationary fluid. It produces a pressure pulse. All right, so now that pressure pulse travels at a sonic speed c, where the fluid over here is stationary and doesn't know that the piston over there moved. It doesn't know my tongue moved yet until it gets to that gets to your eardrum, and then, oh yeah, he spoke. Okay, so it's quiescent, it's at enthalpy, pressure, and density, but behind it, it felt the effect of that change in the piston velocity, that abrupt pop. And it has a change in enthalpy, the pressure is P plus delta P, and the density is rho plus delta rho. So what does the velocity look like? Well, behind it, it's all V, or delta V greater than 0, and above it, or front of it, 0. And then the same with the pressure. It's a P, regular pressure, in front of the sound wave, and then behind it, it's P plus delta P. So you consider a little control volume enclosing the wavefront, and that control volume is moving at the same speed as the wavefront. The control volume is not accelerating. The wavefront's not accelerating or decelerating. So since it's a inertial system, you can do a mass balance and energy balance for that system. Actually, even more than that. So from the perspective of the front and the volume around it, there's fluid flowing into it at constant speed c on the right side. And on the left side, it's flowing out at c minus delta v. And you have enthalpy, pressure, and etc. So you do a mass balance for this control volume. Does that look good? Mass flow rate in on the left is equal to mass flow rate out on the left, in on the right. So then you have, this is rho AC, so rho AV, or the velocity, and then you neglect higher order terms. I mean, if I have d rho, whoops, let me write it right here, d rho times dv, in the expansion of these terms, neglect it. You neglect higher order terms. Is that concept familiar from your 3-hour class in numerical methods? A whole semester in numerical methods. You should have, one of those main themes coming out of it. It's like you have a Taylor series approximation or a Maclaurin series approximation, and then you neglect higher order terms to get a linearization, and then you use that to solve problems. All right. Energy balance. You do the same thing. You have the enthalpy and the kinetic energy, the enthalpy kinetic energy, and then you can just do the algebra, neglecting the higher order terms, and you come up with this equation. You use basically an entropy balance as your third balance, but here we just express it as a TdS relationship about entropy, and then we say it's isentropic. So delta S is 0, so I have another relationship. So I have this equation, this equation, this equation from mass balance, energy balance, and if you'll allow me to say entropy balance. We combine those, mass, energy, and isentropic restriction, to get just c squared is equal to, it's a little bit of just algebra at that point. But it's the rate of change of pressure with respect to density, and you recall S is constant, hence there's the quick derivation. It's all mathematical. Okay? Okay. Now, once you have this, you say, well, I want to work with an ideal gas undergoing isentropic process, of course. Isn't this PV to the K is equal to constant for isentropic? Yes. So we can put P is equal to constant times rho to the K, which is inverse of specific volume. Then I could take the derivative of that, holding entropy constant. That's in the basis of the equation. I can then use that to substitute right here. And I find that C squared is KRT, or C is the square root of KRT. This is an assumption. It's only for ideal gases, square root of KRT. So if I increase the pressure a little bit of the air, it doesn't change the speed of sound. But let's say somebody's at a party and there's a balloon and they want to inhale and then they like to talk. And it sounds really funny, doesn't it? I've never done it. I've never seen it happen. I just heard about it. But it changes the sound because they're speaking in something different. Did they really change T? Did they really change R or K? What did they change? R, right, by the molar mass, R bar. Now, if it's helium, they also change K a little bit, but it's primarily R. True? True. Mach number. So we use this in this textbook MA for the Mach number. If the Mach number is really small, less than a 0.3, typically the compressible effects are neglected. It's treated as incompressible. Incompressible. Even air. Unless you really start moving air, a lot of times you can treat it as incompressible. Professor, if we heat it up, doesn't the density change? Yeah, but not due to pressure effects. It's just, so a lot of times when you go and study HVAC with heating, ventilation, air conditioning systems, you're heating up the air and you're cooling it down. The density is changing, but the pressure change is so small. It's not, you're not changing the density because of increase and decrease in pressure. It's because of increase and decrease of temperature. All right. If subsonic, all that means is the Mach number is less than 1. What does sonic mean? Mach number is equal to 1. What does transonic mean? Well, it's around 1. A little above, a little bit below, but it's not significantly below and it's not significantly above. What is supersonic? No, it's greater than 1. And then hypersonic, much, much greater than 1. So those are some terms you'll see people use. Transonic, supersonic, sonic, hypersonic. Do we have any conditions where things, the goal is to make something be hypersonic? Very much. Especially if you want to shoot something out of a barrel and quickly get over there and hit a target. So this hypersonic flow coming out of a lot of barrels. Okay, also, I think a couple years ago, I should have looked this up, but I recall that the Department of Defense tried an experimental aircraft that was going to be hypersonic. I think they were trying to get to 6 or 7 Mach, and it failed. But hey, sometimes if you're not going to try, you'll never get there. So, does anybody recall that in the news? You do? What was the Mach that they tried to get that aircraft to?
It was around
6 or 7. Yeah.
Like an arrowhead, right?
Very high Mach number. Very high. Incredible. Okay? So, they'll be able to see, they'll learn from the failures and press forward. It may not be as practical. I mean, for a while you could fly a commercial aircraft to France, supersonic. You could spend the money for the seat in it, true? But I don't know if that is as popular as it used to be. I think the cost is high.
I think they shut that down.
Yeah, I think they shut that down.
Yeah, they call it Concorde?
Concorde, yeah. Did you ever fly in one? No. Anybody in flying one? No. Well, you're going to be able to buy a plane ticket or a rocket ticket up into space. People are selling them, so I don't know what they cost. a lot of money. So now let's talk about this device. This device, let me look at it. I have inlet flow at 1, outlet flow at 2. All right? I want to know what I call this device. What is the name of this device? It's a nozzle, and it's a subsonic nozzle. Because now we're going to start talking about compressible effects and supersonic flows, but this is as a little review of what we know about subsonic nozzles. Okay? Because it's bad to launch into supersonic nozzles when you don't understand the subsonic nozzle. Isn't it more difficult? So what about the area? The area 1 and the area 2. This is the easiest of the questions. Does the area go up or does the area go down for the nozzle? In the direction of flow, does the area go up or down? It goes down. And so the exit area is less than the inlet area, true? This is one way of expressing it. This is another way of expressing it. I hope you feel comfortable with both of those. Now, what about, let's say, the velocity of in and the velocity exit? Does the velocity go up or does the velocity go down? the velocity goes up. True. So V2 is greater than V1. All right, what about the pressure at 1 and the pressure at 2? Drops. Okay, so the pressure 2 is less, so the pressure goes down. How about the entropy, S1, S2? Notice, this is geometry. The rest of these are properties. Properties, right? We're just talking about properties. So what about entropy, S2, S1? We're going to assume it's internally reversible. Then it's equal. See? So it's isentropic. So this S is a constant. It's isentropic flow. That's the traditional assumption. Now, you can define an isentropic efficiency for a nozzle to account for some friction effects, etc. But let's just say we have isentropic. Sigma is equal to 0, no entropy generation, S constant. How about the temperature in versus the temperature out? Does the temperature go up, temperature go down? What's the temperature do? Stay the same, constant? Okay. Think it's down? All right. Let's do this. How about the density? Those are all related to temperature and pressure. Isn't density equal to RT over P? So if I'm interested in 1, then I'm interested in 2. I need to know how the T2 and the P2 changed. If I knew how the temperatures and pressures changed, I'd know how the density, as well as the specific volume changed, which is 1 over the density, isn't it? So these are how about the kinetic energy versus kinetic energy 2? Yes, that's correct. Because the kinetic energy is 1/2 V squared, V1. And so the exit speed, V2 is greater. So you square it, and it's still greater, okay? The kinetic energy exit, so the kinetic energy goes up. What about the enthalpy, H1 versus H2? Equal? Okay. Let's do this. Time for a clicker question. The enthalpy 1, let me answer A, is equal to the enthalpy 2. Answer B, the enthalpy 1 greater than the enthalpy 2. Answer C, enthalpy 1 less than the enthalpy 2. And we'll stop there and let you choose. Oh, I didn't start it, did I? Well, did everybody have enough time to answer? Let's see where we're at. Okay, now let's do this. Before I spill the beans, what does this dashed line indicate? It's a little symbol for CV, control volume. What can we do with the control volume? Mass balance, energy balance, and we could do entropy balance. 3 balances. Now those balances could account for transient effects as well as steady state. Almost all of our problems are steady state, right? So for the mass balance, what type of equation do we get? M dot in is equal to M dot exit. M dot's equal to M dot. For our energy balance, I know that we could have the most general form, transient, heat transfer, work transfer, no heat, no work, steady state, no changes in elevation. What does it boil down to? Enthalpy plus kinetic energy is? Does that equation make sense to you? Yes, it does, right? All right, so I'm asking about how H2 differs from H1. Is that equal to, H2 minus H1, is that KE1 minus KE2, or negative the change in the kinetic energy? So if the kinetic energy, did we answer this question right here? What happened to the kinetic energy as it flowed through the system? Did it go up? Did it go up? Okay, can enthalpy remain constant? Okay, this negative sign says that if kinetic energy goes up, what does the enthalpy do? It's going to go down. So which of these is correct? B. Congratulations to the 21%. True? Does everybody understand why? Let's go back and talk about temperature, because we never finished temperature, right? Well, first of all, this is wrong. What does it do? It goes like this. The enthalpy goes down. Tell me a little bit. Let's do it now for temperature. You can redeem yourself. Temperature 1 is equal to temperature 2, temperature 1 less than temperature 2, temperature 1 greater than temperature 2. Start the clicker question. All right, we're in, so I'm going to stop, and we show the results. So what is it? It's getting cold. Is that it? So T2 is less than T1, true? Why is that true? Because when I say ideal gas, it's PV is equal to RT, U is a function of temperature only, enthalpy is a function of temperature only, true? Does the enthalpy as a function of temperature, does it generally go up with temperature? Or does it go down with temperature? Usually goes up with temperature, yeah, true? Yeah, so there you go. Let's go back to this equation. Some people said, hey, I didn't really understand why the pressure would change that way. How about this? It's isentropic flow. Is T2 over T1 equal to P2 over P1 to the K minus 1 over K for flow through that nozzle? Air, isentropic, yes. Could I then say that P2 over P1 is equal to T2 over T1 to the K over K minus 1? Would that work algebraically? So what is T2 over T1? Is that less than 1? Less than 100%? Like it's 0.9 or something? 0.9 raised to the power 1.4 over 0.4? It's less than 100%. So this whole thing would be something less than 100%. So P2 is less than P1. Is that what we had? We confirmed it. That's great. Now, you have to go and work with the densities. You would just come over here and do that with the density as well as the specific volume. Okay? Yes, sir.
And also is, right?
That's correct. You have to have a pressure difference. Otherwise, it's not going to work. Let's solve a problem. We have a converging nozzle. The inlet air temperature is 300 Kelvin. So I'm going to talk about the temperature in 300 Kelvin. Here's our nozzle. Inlet state 1. That way it flows. Outlet state 2. And has a pressure inlet of 120 kilopascal. It exits at a pressure 2 of 100 kilopascal. And the exit area is 10% of the inlet area. So inlet area is unknown, but area exit is 10%, 0.10, times the inlet area. Right? Okay. Continuing to read. The flow is isentropic. So S1 comes in, S2 goes out. Guess what? S2 is equal to S1. It's isentropic. S equal to constant. Use constant specific heat of C sub P equal to 1.005 kilojoules per kilogram Kelvin and a constant K of 1.4. Determine the exit temperature. So I'm asked to find T2. I'm asked to find this temperature right here, T2. I want to know the exit speed. How about if I come down here and I say V2 is what I'm asked to find, right? V2. And the exit Mach number, MA2, and I come down here and I say, I don't know, some exit Mach number, MA2. Well, if I could find the speed of sound at the exit, then I know I would do the ratio to get the Mach number. So it looks like I'm going to want to calculate C2 along the way. Okay, well, how am I going to find T2, V2 Mach number? So we have a control volume, you do the entropy balance, or you just exploit the final result about the how temperature and pressure change for isentropic process in ideal gas, which is the equation that T2 over T1 is equal to P2 over P1 to the K minus 1 over K. True? That's what you do. You know the ratio of the pressures, and you know the temperatures. Guess what this temperature T2 comes in at? 284.8 Kelvin. Colder. Went from 300 down to 284. Okay. How about the next one? How do I calculate for V2? It won't be as easy. Yeah, do two things. Write a mass balance and see how far it takes you. You're going to find you'll have a mass balance, one equation, with two unknowns. I wish I could get another equation. Energy balance. You got the game. That's it. That's it. Just do that, right? I got another equation. Guess what? You'll get the two same unknowns if you work at it a little bit. Now I have two unknowns and two equations. They won't be linear. They'll be nonlinear, which means, okay, you have to have some insight as to how to manipulate it to get the one equation, one unknown by combining them, and then solve for that unknown, then back substitute to get the other unknown. So let me just outline it for you. Mass balance, energy balance equation. What's the mass balance? Says m dot in is equal to m dot exit. Well, how do I calculate the mass flow rate? Isn't it the rho density inlet, area inlet, velocity inlet equal to rho exit, area exit, velocity exit? So, okay, the density of air, is that going to be pressure divided by RT1? Pressure to RT2. I can cancel the R's on both sides. And now I get finally an equation. It looks reasonable. I'll have it like this. Maybe I'll do it like this. V1 is equal to V2 times P2 over P1 times A2 over A1 times T1 over T2. Now, I know this, but I have two unknowns. V1 and V2 are my unknowns. I have one equation. I can work with that until I'm blue in the face and I won't get anywhere. I've got to go get another equation. Energy balance equation. We start the energy balance equation, which is H1 plus KE1 equal to H2 plus KE2. True? And then we manipulate H2 minus H1 is equal to minus KE2 minus KE1. You don't need to put the minus sign in there. I mean, you just need to be algebraically correct. Okay, I put C sub P, T2 minus T1. Why did I do that? I was told to. It makes it so I can do things analytically. All right. So then what I do is I can minus 1/2, or just get rid of the minus sign, 1/2 B1 squared minus V2 squared. Take this for V1 and substitute right there. See that? Now I got my two equations. Now I'm trying to solve them. So I take the one out of the other and substitute into the other. Then it'll be an equation only in terms of V2. And then when you do just a couple steps of algebra, you get 2 specific heat, T1 minus T2 divided by 1 minus P2 over P1 times A2 over A1 times T1 over T2, square root. I didn't say it was pretty. It's just doable, right? Now, boom, I plug it in and I run the numbers and I find that the exit velocity V2, 183.2 meters per second. Somebody has solved a problem like this before, and they recognize a place where students make a lot of errors. Or at least they probably remember where they made an error, and then they look at this and they say, okay, I want to make sure and not make an error right at this step in the calculation. Where is that potential error spot? CP? Why is that a potential error spot? Well, look at the units on CP. It's a units issue. Kilojoules per kilogram Kelvin. When I multiply by the change in Kelvin, the Kelvins go, but I've got a kilojoule over kilogram, right? And then I want to take the square root of that, and I want to answer in, what units do I want to answer in? Meters per second. I'm just going to close my eyes and hope for the best that the units work. No, 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 no. Right? You've got to remember your favorite unit conversion. 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram. True? Have you gotten burned by that? You know, sometimes I think engineering is just, you know, kind of like, oh, you made a mistake. Here's a painful lash. Psh, all right, I won't do it again. Yeah, it's so painful. That's right. Yeah, true? And you get conditioned, like no silly mistakes. No silly mistakes. A friend of mine worked at Holt, I think it was, where they do the diesel. He's a big, heavy diesel mechanic. And they get paid by the job, not by the hour. And when they make a mistake, you know who eats it? He does. You know how many mistakes? He hates mistakes. He doesn't want to stay late till 9, 10, 11 o'clock at night for no pay to fix his mistake. He doesn't want to come in on Saturday for no pay, work all day. That's a lot of people are like that. Engineers are like that. We can't. Anyway, I'm over my time. Thank you very much for your attention. We'll continue here next time.